So we found that a lifetime of a star decreases with the square of its mass because the more massive a star is, even though it has more fuel, it burns the fuel at a faster rate. Now let's turn to the question of what exactly is this fuel. This fuel, of course, is the fuel for nuclear fusion. So what we're talking about is nucleosynthesis. A nucleus is always found to be less massive than the combined individual masses of the protons and neutrons that constitute the nucleus. We're going to call the protons and neutrons the nucleons. Thinking in terms of energy mass equivalence, this observation means that for the nucleons, being bound in as a nucleus represents a lower energy state than being free. So we can expect that free nucleons, when fusing in a bound nucleus, is a process similar to a system jumping to a lower quantum state, with the energy difference getting radiated away. So when a nucleus is formed, this binding energy is released. This graph here shows the average binding energy per nucleon versus the number of nucleons in a nucleus. As you see, it starts to increase as you go up, and up to this plateau here on iron. Now, how much energy is this? If you define the atomic mass as A and the atomic number as Z, then a nucleus has Z protons and A minus Z neutrons. The binding energy then is the difference in mass between the nucleus and its components. The mass in protons is Z times MP, where MP is the mass of the proton, plus A minus Z times Mn, where N is the mass of the neutron, minus the mass of the nucleus when it's formed. So it's the mass before they're bound and the mass after they're bound. This is the difference in mass. The energy that is liberated is this difference in mass times the square of the speed of light. This is the binding energy. This energy is liberated if the nucleons fuse. So let's see here how much energy is liberated if you fuse 4 hydrogens into a helium nucleus. So the mass of the proton is 1.6726 times 10 to the minus 24 grams. And the mass of the neutron is slightly larger, 1.6749 times 10 to the minus 24 grams. So if you sum 2 protons and 2 neutrons, the mass of the constituent is going to sum up to 6.695 times 10 to the minus 4 grams. That's the combined mass of 2 free neutrons and 2 free protons. The mass of the helium nucleus is actually 6.646 times 10 to the minus 24 grams. So the difference is about 0.7%. So if you multiply this difference by c squared, you find that the binding energy of the helium nucleus is about 4.5 times 10 to the minus 5 erg. Now this is a disturbing result. Remember that an erg is the work done by a force of 1 dyne over the length of 1 centimeter. And the dyne itself is the force that results in an acceleration of 1 centimeter per second squared for 1 gram of mass. Now we're talking about 1 gram of mass and the length of 1 centimeter. These are everyday microscopic human scale units. 1 gram of material has of order of 10 to the 23 atoms, the Avogadro number. It's more than the total number of stars in the known universe. And yet, the binding energy of a mere 100,000 helium atoms would be enough to steadily accelerate this huge amount of atoms over human scale distances. The binding energy of a single helium atom can accelerate 10 to the 18 other atoms to 1 centimeter per second and sustain that acceleration for 1 centimeter. Bottom line is 10 to the minus 5 erg is a huge amount of energy for a single atom. And yet it looks small, like written in a human scale like the erg. In fact, a more insightful unit in particle physics is the electron volt, which is the energy that an electron acquires in an electric field of 1 volt. 1 electron volt is about 1.6 times 10 to the minus 12 erg. Because of mass energy equivalency, electron volt over c squared is a unit of mass. The c squared is usually dropped, and electron volt is used as a unit of mass. The factor c squared is implicit. In these units, the mass of an electron is about 0.511 mega electron volts, and the mass of a proton is about 938.28 mega electron volt, so about a gig electron volt, and the mass of the neutron is about 939.57 mega electron volt.